Solve problems.
Oh my gosh.
It's not doing it. We're not. Like I need to. You have like that genetics.
Hi, good morning, everyone. Nice to see you here this morning. Let's get started. I know there's still probably a few people making their way in, so I'll kind of stall for a little bit as I usually do for the first 5 minutes, but I'll make a couple of announcements and then we'll get started with the class today. So announcement number one is, some of you probably noticed I made a big deal about the fact that there was a free copy of the textbook available at the library. There always used to be. It appears to no longer be available online at the library. I don't know if this is an issue with the publisher or if it's an issue with the library. There are copies of the actual second edition at the library, but they're not in stock. Well, stock's not the right word. They're not available because they've been taken out. So under the course outline, if you would like, there is a copy of the first edition, the one that I said would be available for students. So there's a PDF copy of it there. So if you want to still use the first edition, again, the second edition is recommended from 2020. It has new material and new content, but about 80% of what this class is going to cover is also covered in the first edition. And a lot of the new content is stuff that's on slides. And there's even new content that isn't in the second edition because 2020 was 6 years ago. So I'm adding stuff for elections. So if you don't want to purchase the textbook, you can get by with this free one. I can't make the second edition available for free. That would be a copyright violation. Actually, this is also a copyright violation. And it feels less bad because it's the older edition. It's floating around. So that seems clear to everyone. So you've got that there. That was announcement number one. Let's go to our slides here. And we'll start our slideshow. Move this out of the way, fine. Don't show. And then I want to hide. So we need to go. There we go. So, okay, so those were the two announcements that I had to make today. The second is the one that I just made. Text is available on Brightspace. The first announcement, which I'll remind you at the end of today's lecture, our first quiz is next week. I'll talk a little bit more about it at the end, but the quiz is a multiple choice quiz. It'll be available on Brightspace. I think there's 12 to 15 questions, multiple choice. It's not terribly difficult. It's not timed, so you can take as long as you'd like to research each question in depth and determine what the correct answer should be. That makes it sound like they're fairly easy points to earn, and in fact they are. But all four quizzes together aren't really worth a terribly large amount of your time. These are a way to study. They're a way to make sure that you've understood the material. It'll cover a range of everything from the first class last week, this class, and also next week's class, because the quiz will be open at the end of the class. So there'll be 3 classes worth or 3 units worth of information on that first quiz. It's available as soon as the class is over at 12:30, and it will close at 10:30. So make sure you take it sometime. If you think you're going to need 15 minutes, make sure you start it sometime before that 10:30. Yeah.
And once you answer a question, you can't.
They used to be linear, but I guess given the format of this quiz, where I've kind of just made it open book, open note, open universe, and untimed and everything else, I really don't see any particular reason to make it linear, in the sense that, like, what cheating might discouraging by making it linear. So you've already got access to everything. I would, if I can remember, I'll change it so it's not linear. That requires me to go into new settings on Brightspace. So you should be able to go back and forth and answer all questions. I don't intend for this to be a quiz that people would not score well on. I intend for this to be, yes, I understand the material. I can use this to help prepare for the exam. And in doing so, I will earn a very small amount of points towards the final. Does that seem fair to everyone? If you forget to do the quiz, there is no makeup. If you forget to do the quiz, however, I drop the lowest one. Given what I've sort of explained about the nature of this quiz, I would assume they'd all be pretty high. So if you missed one, that 0 would be the lowest one, and that would be the one that goes. If you missed 2, then you would have a 0 in there, but it would be fine. Any other questions about that before we go on? Okay, that were the 2 announcements that we have. See if I can get this to advance. Let's review some material. I usually like to start with a little bit of review. It won't be very long. My intention is to finish class today sometime around 12:10 or 12:15. And I'll try to stay on schedule. So we framed a lot of our discussion last week about System 1 and System 2. Keep these 2 things in mind. Now, this is a big theory in the sense that it covers a lot of ground. This idea of a fast and a slow way of thinking has kind of been part of cognitive psychology and even philosophy for a while. This isn't a new theory. And it's not a very falsifiable theory either, because anytime you do something fast, you say, well, that's System 1. And anytime you do something a little bit slower, you say, well, that's System 2. And anytime there's an error in what you would think would come from System 2, you say, well, System 1's getting it. So it can be a challenging theory to falsify, but it helps to frame a lot of the discussions we're going to talk about. And we'll come back to this a few times today. We'll come back to it a few times over the next few weeks. And the general idea is that our fast system, the fast way of making decisions, solving problems, et cetera, relies on areas of the brain that are relatively evolutionarily more primitive. In other words, fight or flight systems that are shared by other species, other non-human species. It's fast, it's intuitive, and System 2 is slower, reason-based, language-based, and seems to be unique to humans. So it's the way that we think using our language, and it just takes longer. It takes longer to use language when you're your way through a decision. We'll come back to this in a lot of ways. So in last week's class, we covered some challenges to the thinking process. I'm going to review this 2 ways. First, I'm going to ask everybody to remember what those are, and then I'll review some of the foggiest concepts, things that came up in the QR code. So what are at least 2 of those challenges? We talked about 3 challenges, but what are 2 of the challenges? So what can you remember from last week?
Multitasking and cognitive offloading.
Okay, so multitasking and cognitive offloading were 2 of the challenges. So those are 2 that I talked about in the textbook. I've since added a 3rd challenge, which is kind of a combination of these. So the brain rot idea, in a sense, kind of builds on some of these. Why are these challenges? So first, multitasking. What's the challenge with multitasking? Why is it a challenge to a thinking process? You think it would be good?
Well, think about more things. As we saw in one of the experiments, you might end up being more susceptible to distractors. Yeah. Which take away from focusing on one particular.
Okay, great answer. So if you didn't hear it in the back, if you're focusing on more than one thing, it takes away from your ability to do both of those things. So you pay attention to things that may not be relevant. And there's also the switch cost. As you switch between different tasks or 3 or 4 different tasks, there's some time delay. It takes you time to pay attention to the first thing and not to the second. So you're sitting up near the front. I just heard a ping notification on somebody's phone or watch. That's an easy distraction right there. I'm not trying to shame anybody because my watch goes off all the time with all sorts of things. Forget to put it on do not disturb. That's what I mean. So even if you're not paying attention, there's a thing that we've been conditioned to pay attention to. That ping doesn't really mean anything to us evolutionarily, but we've attached some significance to it. So when your watch buzzes or your phone buzzes, you now know that that means something, and that takes your attention away. That's the kind of multitasking that can be really hard to avoid. And that's why it's a challenge to the thinking process. The second one, what was the second one again?
Cognitive offloading.
Cognitive offloading is another challenge. So what is cognitive offloading? Why is it a challenge?
Because we're all floating onto external sources such as technology.
So you offload some of your thinking to external sources. This could be a challenge because what if you lose those external sources? What if you lose access to some of the things? If you've written everything down and you've forgotten your notebook, then you no longer have access to that information, which then leads to sort of a larger challenge to the thinking process, which is making decisions and solving problems with incomplete evidence. If you don't have access to the information that you need, then your decisions will be less well informed. If you've written stuff down or you've cognitively uploaded to your phone, and now you don't have a phone, then you're going to have the information that you need. How many of you remember the great Rogers outage of 2023? Do you remember that? Even the weekend couldn't perform in the Rogers Center that day because Rogers internet went out. Nobody knew how to do anything for a couple of days. Nothing could be done unless you were on Bell. It was kind of frustrating. And every so often, Office 365 here at Western, your email goes down. Can't get anything. Right, I can't log on to stuff. Every so often, if Office 365 is down, you can't get onto Brightspace. And if you can't get onto Brightspace, how can you get your course notes? So we've really become dependent on a lot of this. And so we need to consider that as a thinking challenge. There were a couple of others that were mentioned. We talked about the brain rot is one. That's one of the ones that I'm going to talk about in just a minute. Another way to, now I don't understand why this word laptop begins with an L and then says app top. That's not helpful. So here's an example of a question that I might ask, not on a quiz, but on an exam. We talked about some experimental conditions with a laptop. So this is in this larger multitasking discussion. So multitasking sometimes means having access to a laptop. Cognitive offloading also means sometimes offloading your note-taking to a laptop instead of maybe writing, which might be a different way to offload. What were the experimental conditions in those laptop studies? In other words, what were the independent variables? What did the experimenters manipulate in that study? Yes.
I don't remember, but I was saying some of the experimental conditions were like your phone being right beside you, or your phone being like outside
Phone being outside, being
Nice.
beside you.
the classroom.
Different study, but correct. That would be the phone study. So the phone study, you've got phone other room, phone in your bag where you would normally put it, and phone in front of you. There was a laptop study we also talked about in which participants took notes. Anybody else has a guess on this one? Yes.
They listen to a TED talk and they have to take notes on a notebook or a laptop, and they were quizzed after on like general content questions, like more explanation-based questions.
Great. So good. So the laptop study. So this was the pen is mightier than the laptop. What's the name of the paper? So in the experimental conditions, you watched a TED talk and you took notes either on your laptop with no internet or on paper and pencil, sort of conventional note taking. And what we found, well, we found a couple of things. So then they answered some multiple choice questions, some easy and some hard multiple choice questions. Is my next slide. What did they find? No. What did they find? We talked about two experiments. Experiment 1 and 2 were the original study, and then we talked about a replication study. What were some of the consistent findings between the first study and the replication study?
People in the laptop group and their notes verbatim, but on the quiz that they took, they didn't recall as much information as the group.
Right. So in the first study, in the original study, so if a question on an exam says in the original study, participants who took notes on their laptop wrote more and they transcribed more verbatim overlap, but they didn't do as well. They retained less information about what they had seen. Their note-taking led to less good performance on the more difficult multiple choice questions. So the ones that required some application. In the replication study, what was different? How did the replication study differ?
There weren't any significant findings between, like the difference between taking them on a laptop versus by hand.
So they didn't find the same significant result, but which ones did replicate and which ones didn't? You remember? Yes,
It was like the verbatim stuff replicated and the fact that people were more.
yes.
But then there were like mixed findings on whether they performed better on application questions or.
Wait, so they did replicate the people write more on their laptop. They failed to replicate over many different studies. So this meta-analysis, they failed to replicate the finding that people who took notes on their laptop did not do as well. There was no difference between the hand note takers and the laptop note. This is still work that's in development. And one of the things that came up in our question last week was whether or not taking notes on an iPad with an Apple Pencil would have the same benefits as writing, but also maybe some of the same benefits as having an electronic device. Presumably, it would have the same benefits as writing. We also talked about the possibility of cohort effect. I think I had this discussion with somebody after class. That is, how many of you have ever taken a lot of notes by hand? Or have you almost always in your academic career since high school taken most of your notes on a laptop? How many of you have feel like you're really good written note takers? How many of you feel like you're really good hand or laptop note takers? I mean, it's possible that there are some cohort differences. 10 years ago, when the original study was done, there were fewer people with a lot of experience taking notes on a laptop, and so they took bad notes. And it's also possible that as more people have become comfortable with taking notes on their laptop, the hand note-taking skills have degraded. That most people aren't comfortable taking notes, or many people, not most people, but enough people to make that significantly control. But enough people aren't comfortable taking notes paper and pencil, and so their notes just weren't else. Both of those things could be possible and could cause some of those differences to wash out. And that's maybe one possibility why the result didn't hold up. Forward this was from somebody's note in the, I put all of the topics in the stop here for the foggiest concepts. So I asked, what topics would you like to hear more of next week? Somebody says, how brain rot actually affects our brain. I don't know how it actually affects your brain. Probably doesn't have an actual effect on your brain that's any different from anything else, in the sense that as you learn things, your brain changes. Connections are strengthened, connections are weakened, or as I think it's a common expression you might hear in the neuroscience area, neurons that fire together wire together. So as things happen concurrently, those connections are strengthened. So if you do things over and over again, like a habit or learning something, your brain is going to change. So brain rot isn't unique in that respect. What I mean by brain rot, of course, is having proximal information being. So if you're spending a lot of time developing habits that are not really good for thinking, or that cause you to learn things that you don't need to make decisions, then you may have a lot of information at your fingertips that's not very helpful. Can you clarify what incomplete evidence as a challenge to thinking? I'm unsure what the challenge is broadly and how cognitive offloading is related. Let me get to that in a minute. And then in chapter 1 reading, the frequency of events is mentioned and how it skews our judgment. They did not really understand that. Maybe it's just the wording. Well, could you explain this section? Thanks. And so with respect to the second question, incomplete evidence, we talk about incomplete evidence. Incomplete evidence is kind of a broad category. It relates to cognitive offloading. Because if you've offloaded things, you're less likely to encode them and have them at your disposal when you need them to make a decision or to solve a problem, which means you're more likely to have incomplete evidence. And so that might be one way to connect those two concepts. With respect to that third question, the idea of frequency, I looked up in the textbook on page 11, so it's talking about the availability heuristic. We're going to talk about availability heuristic today. We're going to talk about it quite a lot because it's one of the fundamental heuristics in the psychology of thinking. The basic idea of availability is that we tend to make decisions, make judgments, solve problems, etc. We think about things if we have available evidence. In other words, the information that's proximal, what you can bring to mind to solve a problem. One of the heuristics that we use mentally or cognitively is that if we can recall something easily, something comes to mind really easily, the information that you need, that ease with which you can recall something is often taken as a cue that it's the right information. In other words, you trust your memory. If you remember something, if you're trying to make a decision and you remember the information, if it comes to mind really quickly, you think, well, that must be the right information because I remembered it really quickly. If it happened recently, you're likely to remember it more because it was recent. If it's the right information, great. If it's the wrong information to make a decision, then you might make an error. That's an example of a type of availability called recency bias. If something is highly salient, in other words, if it's really meaningful or if it was impactful, it might skew your judgment because you might recall that information more easily because it was very salient. Does that make sense to everybody? So what I wrote was, I think this is what the person was referring to. However, events that are perceived as being more frequent because high salience or recency will skew our judgments. I can see why that wasn't clear, because although those are English words, this appears to be a completely incoherent sentence. I have no idea what that sentence means. So if I'm reading that, I would say, what? I don't understand, which is exactly what the person said. I don't understand. So this appears to be a writing error that made it through my proofreading and the editor's proofreading and made it into print. What it should have said is something like, however, events may be perceived as being more frequent because high salience or recency will skew our judgments. In other words, we might think things are more important because they are higher in salience, because they have them always. And that will skew our judgment. This will all seem clear as we talk about availability in more detail. But if you were troubled by this particular sentence, I really appreciate you reading the text that carefully to point out that there is, in fact, something that doesn't make sense in this. So I'll make a note to this so that in subsequent versions of this text are printed, that bad sentence. Does that seem clear to everybody? Okay, so let's talk about similarity now. So that's the main topic for today. We're going to talk about what it means for things to be similar, why it's important for thinking. And then in the second half of today's lecture, we're going to talk about theories to understand similarity. So let's start with a general question for you. How do you define similarity? What does it mean to you if you were to say these things are similar? Not the same, but similar. What does similarity mean behaviorally, psychologically, mentally, etc.? Yeah.
Like there's an overlap between like the features that two things have.
Okay, so that's a great definition. There's an overlap. Things might share features. Apple and a pear might be similar because they share features, right? What are some other ways to describe or define similarity? What else might similarity mean? Featural is one really strong one, and we're going to talk about a lot of featural.
The function of something, like if you use two things similarly, like tweaks to like you would use them.
So functional similarity, you use things the same way. If I have one of those silicon spatulas to stir something, it doesn't look at all like a metal spoon, but I can use them in the same way. So I could say they have a similar function. They look completely different, but they're doing the same thing when I'm cooking. So those have a similar function, and I would say, well, those are a lot closer to each other than a knife. So maybe my cooking knife is also stainless steel, same material as the spoon, but they're not functionally very similar at all. So on the surface, there are some differences, but the function is the same. What are some other ways to define similarity there are? It's an open-ended question. I have no idea what the right answer is.
Two things or people could be like behaviorally similar. So like they might act in similar ways, but it might not be identical.
So people might act in similar ways. They might behave in similar ways in similar situations. And then, of course, we have to define similar situations. Might be featural, might be functional, might be behavioral, etc. Any other suggestions for how we want to think about similarity?
Kind of similar, but two or more things that evoke the same response.
Evoke the same response. So this is a really clear behavioral definition, an operational definition of similarity, which we'll get into, which is, and I would call this, when we talk about concepts, we're going to define a concept as a behavioral equivalence class, a group of things that, although they're different, you respond to them in the same way, you behave towards them in the same way. So we might have different things that we can eat for breakfast. They don't look the same. They're not made of the same things, but we eat them for breakfast. So they're similar because they're breakfast foods. Does that make sense to everybody? Okay, so let's start with an example. This isn't quite a case study, but this is an example of a kind of similarity. And the reason I like this example is that it reflects on a lot of different things about the psychology of thinking. We're going to talk about expertise. We're going to talk about surface similarity and deep similarity. And we're going to talk about the way in which similarity and perception are tied together. This is from a podcast from 2016, and it's called Something Only I Can See. The podcast is called This American Life, and it's an old podcast in the sense that it was around as a radio program long before podcasts became a thing. So it's worth listening to if you want to hear sort of the in-depth description. But what it's about is a woman who lives in Iowa. She's the woman on the right. And her name is Jill. And Jill has a rare form of muscular dystrophy, which is why her arms and legs are very thin. And what Jill noticed at some point is that she saw a Canadian sprinter, Priscilla Lopez Schleep, and an Olympic sprinter. Is anybody familiar with Priscilla from 2 Olympics ago? Gold medal Olympic sprinter for the Canadian team. And when she saw a picture of Priscilla, she said, "You must have the same genetic background. There's something about us that is the same, and that we must have a similar illness. Whatever it is that caused the atrophy in my muscles is the same thing that Priscilla has." And most people didn't take her seriously. Because you would think, well, the woman on the right doesn't look at all like the woman. There's a lot of reasons to think why they wouldn't be similar at all. In addition to one of them being an Olympic athlete, the other one not. The one on the left is kind of, built. And the one on the left, the one on the right is not kind of built. Here's how Jill describes herself. 2 photos. This is this is an article that was written alongside it. Jill out to right. Jill in a royal blue bikini sitting at the beach. Her torso looks normal, but her arms are spindles. It couldn't be skinnier, like sticks jabbed onto a snowman for arms. Her legs are so thin that her knee joint is as wide as her thigh. Those legs can't possibly hold her. I thought. This is the author of the other picture is Priscilla Lopez Schleep. Priscilla is one of the best sprinters in Canadian history. The 2008 Olympics in Beijing, she won the bronze medal in the 100-meter hurdles. It was the first Canadian Olympic medal in track and field since 1996. In 2010, Priscilla was the best 100-meter hurdler in the world. And so again, why would they be seen as similar? Photo beside Jill is remarkable. Priscilla is in mid-stride. It's difficult to describe how muscular she looks. She's like the vision of a superhero that a 3rd grader might draw. Oblong muscles bursting from her thighs, ropey veins saying, "Love class." This is the woman Jill thought she shared a mutant gene with. I think I laughed looking at the pictures side by side. Somehow, from looking at the pictures of Priscilla on the internet, Jill saw something she recognized in her own much smaller body and decided Priscilla shares a rare gene mutation. Now, Jill is not a geneticist, although she later worked with geneticists at the University of Iowa. She based this decision solely on visual appearance. She looked at Priscilla and said, "We are the same. We have the same genetic mutation that caused my illness and my condition, Priscilla." And since Priscilla doesn't have muscular dystrophy, her body must have found some way to go around it and to make enormous muscles. Well, what does this have to do with similarities? These 2 women are similar. I'll go into a little bit more detail, but to cut to the chase, yes, they do have exactly the same genetic mutation. It was, as you know, about probably a little bit about how genetics work. Genetics underlie these things, but they can be expressed in different ways. And something about the way in which the genetic mutation was expressed in Jill caused the atrophy, and the way it was expressed in Priscilla caused larger than average muscles of a particular kind. So they do have the same genetic mutation. They are the same underneath. What this has to do with similarity is that these 2 women are similar in a deep and fundamental way. There's something genetically the same about them, but it's not apparent on the surface. So one of the explanations we gave for similarity was sharing features. And if we're counting up the features that these women share, they share features, but the features they don't share are the very features that are actually being caused by the thing that they do share, which is the genetic mutation. What this also has to do with similarity is that when people are experts in a certain field, they can often perceive aspects of similarity that non-experts can. You know a little bit more about how things really work, what causal factors happen. So the genetics caused this. An expert in genetics, once this was understood, an expert in genetics might say, well, this mutation, of course, these two women are similar because they share this mutation. Until it was discovered, thanks to some of the work that Jill initiated, only someone with a lot of perceptive ability might have been able to notice these things. Jill points out her dad was thin, but the muscles on his forearm were unusually well defined. Jill would call it a Popeye. So you can't really see it in the picture very well on the slide, but you can see it on your own side. He's a thin guy, but he's got sort of big biceps, big triceps. In another paper, she saw that Emery-Dreifuss patients, this is a type of muscular dystrophy, often have that same trait. It was referred to as Popeye arm deformity, but she didn't see any pictures of women in the disease. She read a paper from Muscle and Nerve, a journal, described 3 hallmarks of Emery-Dreifuss patients. This is the type of muscular dystrophy she has. They couldn't touch their chins to their chest or their heels to the floor, and their arms were perpetually bent. The medical term is contractures. In middle school, Jill's head once got stuck for a while as she was looking up. So you can't look down in a certain way. But a week later, so this is Jill got curious. She started Googling not just pictures of Priscilla running, but she saw the prominent veins, the same fall of clothing over the shoulders and arms also found. The same visible divisions between muscles in the hips and butt. In other words, very low body fat, very high muscle content. It was unmistakable. It's like a computer that can analyze a photo and get a match up to 100% sure that it's the same shoulder, that's the same upper arm. I see the same veins. I see them branching this way. I just know, and it's hard to convey, but you just know. We knew we were cut from the same very rare cloth. It was the 3rd time Jill had made a visual log on something rare. First was with her father when she thought they had lipodystrophy, and now she saw that she and Priscilla must have the same mutant gene because of the exact same pattern of this fashion. So the reason I like this case study, and I encourage you in your spare time to listen to this particular podcast, is that it highlights this kind of weird aspect of similarity, that sometimes you cannot see anything on the surface, and yet there is still something that pulls 2 things together. That's why I think similarity is really important to discuss. But I want to come back to a fundamental aspect of similarity and why we want to study it in a course on thinking. Somebody asked last week, what's the hardest unit? What unit do you think is the most challenging? I think the unit on similarity is probably the most challenging because it seems the least like thinking. If we define thinking as using mental representations to solve problems, to make decisions, this idea of similarity seems a little bit abstract. And it is a little bit abstract, but I think it underpins just about everything else we're going to talk about in this course. When you solve problems, you often remember problems that are similar. So how do you do that? How do you decide which problems to remember? When you make a decision and you have to remember the rules to make a decision, you often have to remember a similar decision you've made. How do you decide what that similar decision is? Do you decide based on surface features, or do you decide based on some kind of deeper feature? If you're deciding what to do, how to maybe treat a particular illness, and you know that there's a genetic mutation, even though it isn't present on the surface, that could be really important to know underlying cause for these types of things. So I really like this example because it highlights this particular quirk of similarity, surface and deep feature similarity, which we'll come back to a little bit later today. So why should we study it? This is something that's covered in the text. First, these are 4 things, by the way. Quick heuristic, if I list 4 things on a slide, it's a great longer answer question for an exam question. If I say I could say, what are the 4 reasons to study similarity? You could just list them, and that would be the answer to that kind of question. Similarity underlies many important cognitive processes, and I'll go through them on the next few slides, but pretty much everything else we're going to talk about has some connection to similarity. So that's one reason why we should study it in cognitive psychology or in a psychology of thinking class. Number two, similarity is what is often referred to as a domain general construct. In other words, it kind of works the same from a computational standpoint, regardless of what you're making the comparisons to. In other words, the computations that you might use mentally or neurally to determine that Priscilla and Jill are similar would be the same calculations you might use to determine that an apple and a pear are similar. So those kinds of computations are the same computations. So it's domain general. It's not just something about fruit similarity and people similarity, but there are some basic fundamental aspects of similarity. So it's general across many different domains. Three, it can be an important diagnostic tool in the sense that it helps us know whether or not someone is thinking about things as an expert or a novice. Jill was thinking like an expert, even though she really wasn't an expert in genetics. She was an expert in her own particular genetic mutation, and she recognized those features in other people. So she thought about these things like an expert in a different way than you and I would. And so it's a diagnostic tool. It can tell you whether or not somebody's making decisions expert-like or novice-like. And finally, it's grounded and very close to perception. Similarity is also something that not only is grounded close to perception, it's close to the physical reality of objects in the universe. Our perception allows us to interpret what we see and feel and hear in front of us and create mental representations. But similarity also works even outside your mind, in the sense that water molecules come together because they're similar. Right? There are physical principles and chemical principles around similarity that allow the universe to organize itself in a particular way. So similarity is a real thing in the physical universe outside of our minds as well. And it's a way to connect what we think about in our representations with the outside physical universe. I'll go through each one of these with some more examples. Any questions so far, though? Does this all seem straightforward? Great. Okay, so what are some of these examples? Let's go through four of them. We're going to talk about object recognition, memory, problem solving, and reasoning. These are all things that we're going to talk about in much more detail in separate units in this course. But let's talk about how similarity is used in each one of them. For object recognition, well, fundamental aspect of object recognition is comparing what you see in front of you with things that you've seen before so that you can recognize this instantly as a pumpkin. It takes almost no effort for you to do that, right? And the way you do it is that you say, well, you don't say this, but your brain says, what I see activates things that I've seen before, and they are the same pattern of activation. And so therefore, I call this the same thing that I've called other stuff that looks just like that. The only way you can have a good object recognition system is to have some way to measure similarity and assess similarity. And that's how you can get the names or the ways in which you want to behave toward them. Any one of these objects can activate some kind of memory, whether it's a water bottle, an ancient cell phone, a CD case, things that you may not even use, like a can opener. Things that are in different coordinations or different sizes. You can recognize them all pretty well because they activate something. And if you've never seen a can opener that looks exactly like this, you've probably seen other kinds of can openers and you're able to identify. It doesn't have to look exactly like something you've seen. It just has to be similar, right? And it just has to be similar enough to something more so than it is to other things so that you can come up with a name. That's how we do memory retrieval. We're going to talk about this next week. I think is next week memory. I feel like it is. Yeah, I should remember this and put the course outline together. So next week is memory. We're going to talk about memory in more detail, but you already probably know this if you've taken an intro course or if you've taken a course in cognitive psychology. A lot of memory is done by spreading activation. So your semantic memory, your memory of what you know, one common theory is that it spreads If you activate one concept, then neural activation or cognitive activation spreads to other areas as a function of similarity. If things are more similar, the activation spreads more quickly and more and stronger. If things are not very similar, the activation takes longer to reach the concept. So if you activate doctor, nurse, hospital, dentist, and fever might be strongly related. Green and glass, green if you have a fever perhaps, is not very strongly related. Green and grass are strongly related, but doctor does not really activate the expression of green. You could get there, but it's not similar enough to receive it as activation. So activation spreads as a function of similarity. If you think of one thing, you think of things that are similar to it as well. You can also make same or different decisions. So decisions about not only your content of your memory, but episodic memory. You can decide whether or not this is the same pumpkin or a different pumpkin. Or you can ask whether or not it's the same kind of fruit. In this case, it is. It's not exactly the same pumpkin because you can probably remember what the previous one looked like. What was the difference between this one and the one before without looking at the slides?
Order.
Different stem. All right, so the stem is different. So depending on what you're asked, are these the same? Yes, they're the same in the sense that they're pumpkins. Are they the same? No, they are not the same pumpkin. They are two different things. So again, similarity has an aspect in different kinds of memory. It activates the concept, but it also lets you know that these two things are slightly different. They're different enough to know that they are different pieces of fruit, different pumpkins. So that seems pretty straightforward. Let's talk about problem solving. Problem solving is a more complex kind of thinking. How might similarity be useful in solving a problem? Well, one way, and this is what we're going to talk about when we talk about problem solving, is through a theory of problem solving known as problem space analysis. So problem space analysis, the problem space theory assumes that when you are solving a problem, you work in a space. You think of it metaphorically, and sometimes it's physically a space. But the space that you're working in when you solve a problem are all the possible things you can do, all the possible decisions you could make, all the possible changes you could make, all the possible moves you could make if you're playing a game, everything. All of those together are the problem space. Some of them help you solve the problem, and others do not. And sometimes you can solve the problem more quickly by choosing the right moves. We talked a little bit about chess last week. The problem space in chess is all of the boards, all of the pieces, and all of the legal moves that could be possible in any particular game. Some of them will help you win the game, some of them will not. Problem space analysis means that you want to find the quickest way through the problem space. Ideal or optimal problem solving chooses decisions or behaviors based on what will help you get from the beginning state, the opening state of your problem, to the end state, which is the solved problem. Similar problems tend to be grouped together now. So there are two ways in which problem space analysis relies on similarity. But for our purposes, and this relates to Jill and Priscilla as well, imagine most of us solve a problem. Let's say it's a math problem, or a computer program problem, or a financial or an investment problem, trying to manage your investments, for example. You might learn the best way to make decisions. So if you're just getting involved in investing, let's say, you might learn some rules about how to distribute or diversify your investment portfolio. What do you want to grow? How fast do you want it to grow? How much risk are you able to tolerate? And those are things that if you're coming to it for the first time, probably have to take a little bit of instruction. You wouldn't want to just go blind and start buying stocks without any particular background, right? You want to be able to invest properly. If you're solving a problem, if it's a math problem or a physics problem, somebody has to show you how to do it first, right? You can't just solve it. Most of us need to be given some instruction. We're going to call that instruction the algorithm. So whether it's a math problem, a medical diagnosis, an investment problem, or anything else, you're usually told how to do it or shown how to do it, or you read how to do it. You discover how to do something. You're given a set of instructions, a step-by-step way to solve a problem. And that gets you the solution. If you follow those steps, whether it's math problem, a physics problem, an investment problem, or a scheduling problem for your next term courses. You're still following the steps, right? If you're doing this a lot, let's suppose you're doing a lot of problem solving in the same area. Suppose you're a physician. You see a lot of people come in with the same symptoms. For 20 years, you've been a physician practicing in London, Ontario, and you start to see a lot of people coming in of the same kind. Eventually, you really recognize what holds them together, almost kind of like how Jill recognized her body type, her father's body type, and Priscilla's body type having something in common. It wasn't maybe obvious at first. Maybe she didn't even know how to explain it. She just knew that there was something there. If you're experienced as a problem solver, you get used to seeing these examples, and eventually, when you solve a problem, you no longer need to use steps. That's the hallmark of intermediate or expert problem solving. You stop relying on the steps and you take shortcuts. And the shortcuts are heuristics. The shortcuts are, I remember somebody like that, and that's how I treated them the last time, so I can diagnose them the same way this time without having to go through all those steps. I remember solving a problem like that just yesterday. This is similar to that problem, so I will solve it the same way today. I don't need to go through the steps. This is faster, and this is almost, well, this is an example of more of a system one kind of problem solving that experts have access to because they have extensive knowledge. This is not the kind of problem solving you can get to overnight. This is the kind of problem solving that would take years of experience. You have the wealth of knowledge that you can do things quicker, faster, and easier from memory than by following the algorithm. How many of you have learned how to play the piano or a musical instrument? And when you first learn how to play, one of the challenges I always had when I was younger was remembering which note is which, right? I mean, notes on the staff, the lines have a heuristic, the spaces have a heuristic, and at first you have to sort of figure out which note is which, right? You say, what note is that? I can find it here, but it gets faster and faster, and eventually you can do it without having to use the heuristic or the algorithm that tells you which space and which line it's named with which note. You just see it and you can play by sight. That's an example of getting faster through experience. You no longer have to rely on that step by step. Now, does that seem clear to everybody? Okay, inductive reasoning. Inductive reasoning is something we're going to spend a whole lecture on because it's one of the types of thinking that we rely on every day. Induction is when you make a prediction about something because it's similar to things you've seen before, but you're predicting features you've never seen. So induction is kind of how our brains tell the future. Your brain can predict the future through induction. You use induction to be able to take what you know and predict something you don't know. So this is a Hubbard squash. Is anybody familiar with the Hubbard squash? I'm actually kind of relieved to see no hands go up because it's kind of a weird squash to be familiar with. I have no idea why you'd be really into Hubbard squashes, but they're kind of ugly. They're about the size of a pumpkin, but not as attractive as the pumpkin. But they're delicious if you cook them. What would you expect to find on the inside of a Hubbard squash? If you cut this gray-blue squash open, what do you think is going to be inside?
A hollowish pit with like seeds on the inside.
Hollowish with seeds on the inside, because if you've ever cut open any other kind of squash, or even a pumpkin, which is also a kind of squash, you kind of know what's going to be on the inside of a Hubbard squash. And there it is. It looks exactly like the inside of any other squash. On the surface, the outside, you might not know, but if you've never cut open a Hubbard squash, you would expect to find squash-like inside. This is not my child. This is just a random photo I Google image searched to say picture of inside of Hubbard squash, and I thought she looked kind of pleased. Probably like 20 now, and wondering why she continues to appear in slides. So there she is opening up a Hubbard squash saying, look, that's the inside of my Hubbard squash. They make an excellent pie, by the way. And so that's an example of induction. You know what's inside a pumpkin because you probably, even if you're not cooking and eating pumpkins, all the time. You've probably carved a pumpkin. How many of you have carved a pumpkin for Halloween type purposes, or at least have seen it done, right? Doesn't have to be something you're an expert in. You just kind of know what's inside a pumpkin. You don't know what's inside a Hubbard squash, but we rely on similarity. They're not similar on the outside, but you know that there's something about them that is the same. And if they're the same on the inside because they're both squashes, you kind of predict this additional feature. So induction relies on similarity. In fact, there's a whole theory of induction, which we'll talk about, called the similarity coverage model of induction. You make predictions on the basis of similarity. Similarity induction model will work if we don't have a good understanding of similarity. We do this all the time with devices. Most of us probably can't remember back to the original BlackBerry, but it doesn't really involve a whole lot of physical overlap with current phone designs, which almost pretty much the same regardless of the manufacturer. So we can see a transformation of similarity from early devices to more current devices. We can also see some offshoots, and we can see some functional differences between Android phones and Apple phones, but eventually they all started to look the same. So there's a trajectory, a transformational similarity, where we know that this device and this device share a lineage. That they're not similar on the surface, they don't function the same way, but they were designed to have some functions that were similar, and they share this transformational similarity, which we'll talk about later today. Okay, similarity is a domain general construct. By that, I just mean it doesn't depend on specific kinds of information. Squash induction and phone induction is the same inductive process. And the similarity you might use to predict how is my new phone going to operate versus my old phone going to operate is the same process you would use to say, how is this new squash going to look on the inside compared to the squash I cut yesterday? Right? It's the same general set of computations. The calculation of similarity works more or less the same way for many things. Finally, I'll do this last one. We'll talk a little bit more and then we'll take a break. Right on schedule. It's grounded in perception and physics. And for that, I just want to do a very quick example. This will come up in a little bit longer as well. But this is from a chapter by Rob Goldstone on similarity, and I'll explain this particular example as we go forward. A final reason to study similarity is that it occupies an important ground between perceptual constraints, that is what we can perceive, and higher level knowledge system functions, what we can think about. Similarity is grounded by perceptual function, a tone of 200 hertz and a tone of 202 hertz, which physically are close to each other in the world of physics, whether you can hear them or not, sound similar. And the similarity is cognitively impenetrable. What they mean by cognitively impenetrable is that we cannot explain why it's the same. We can explain it, but we can't unpack it. We can't drill down to explain exactly why those features act the way they do. We just hear them as the same. Even though there is little that can be done, enough that there is little that can be done to alter this perceived similarity. In other words, you cannot help but hear these two tones as similar. Here's what I mean. So let me go on to this. So what was the first one I said? It's 200 and 202. Let's pick a 200 hertz. Then play it. It's a nice mellow tone, isn't it? It's pleasing. That's a nice vibe. Let's do 202. Does that sound the same? I mean, how could you not hear that as being pretty much the same? They're obviously not the same because you saw me change one from 200 to 202, but they sound the same to us. Even if you know which one is which, if I played them without telling you, you wouldn't be able to tell. If we were to go and pull both of them together. There's our 200. you can hear that the waves don't overlap, which is why they pulse, which is less pleasing. So they're in the world of physics, in the outside universe, outside of your mind, those waveforms are almost the same, but not exactly. They're so much almost the same that they almost work the same way. They're moving air in the same way, but not enough, which is why they don't line up. But when you hear them, they sound exact. The only way you can hear them not sounding exactly the same is to hear them on top of each other. So you can hear that the waves don't actually line up. You can know that they're different, but you won't be able to hear them. That's what I mean by it's cognitively impaired. I can tell you they're different tones, but you can't hear them. You can't help yourself but to hear those two things. So for a lot of what we think about similarity, it seems to exist in the physical universe, even outside your cognitive. Does that all seem relatively straightforward for this morning? Good. All right, let me, I wish I could just get it to make itself big again. Every time I go back into this, you would think by now, well, I would know how to work these things. I've got 3 things to talk about measuring similarity, and then I'm going to talk about some theories of similarity. If we go through these 3 ways to measure similarity, it's going to take about 15 minutes, which will take us till about 10:40. Is everybody with me for 15 minutes, or would you prefer to take a break now and just do a little bit more later? We're good to keep going? Okay. Sometimes just stopping and thinking about things for a few seconds is enough to count as a break, not a real break, but enough to count as a mental break. So if you want to stretch, take a deep breath, stop for a second. We'll do 15 minutes to talk about ways to measure similarity, and we'll take a slightly longer break. Is everyone okay with that? I'm totally fine to do anything. I understand how long this lecture is. I sympathize with you. I would absolutely not want to sit in my own lecture and listen to somebody talk for 3 hours. So do you all have just mostly 3-hour lectures? That's pretty much a default, isn't it? I mean, 3 hours is just a standard lecture. How do you make it through an evening lecture? 7 to 10. Does anybody make it through a 7 to 10 lecture? How many of you have 7 to 10 lectures? How many of you hate 7 to 10 lectures? There's no way I can do it. I can't stay, I mean, I can't stay awake that night, but I cannot imagine sitting. Anyway, I'm just sort of stalling here so that we can concentrate again. All right, back to what we're talking about. Measuring similarity. I want to talk about ratings tasks, forced choice tasks, and sorting tasks. These are just ways in which psychologists can use to measure and assess similarity of objects or things or stimuli. And I want to talk about them because a lot of the experiments we're going to talk about in the second half of this class will sort of depend on these kinds of tasks. So ratings tasks are exactly what you would expect. People rate things as being similar or not. You might see 2 images on the screen and you would give them an answer between 1 and 7. How similar are these things? What would you give this? These 2 fish, these cartoon fish. We've used these in some of our experiments before to learn concepts. I would say these are kind of a 6. I'd give these a 5 or a 6. I feel 5 or 6 makes sense here. And how would you base whatever number you decide to assign this? How would you base it for something like this? Would this be higher or lower? I'd give us a lower number. If you're making the similarity judgment of objects like this, what do? Here's another one. You look for similar features. You can do that because why? Why would you be able to look for shared features or feature overlap?
Because it's like more standardized, like
It's kind of standardized. We can name them. A very important thing here is these are nameable features. Not only are they nameable, but they're separable. We can separate each one of these features. We can say, well, look, I've noticed that these things have tails and the tails differ. If they have different tails, that's a knock against them being similar. If they have the same tails, then that makes them more similar. Here's 2 with the same tails, but they have different body types. So if you do enough of these, you did 4 or 5 or 10 or 100 or 300 trials of these, you'd start to think, well, I think I know how to work in this space. I just count the features up. More features, more similarity. And that's probably what people would do. What about these? How would you rate the similarity of these objects? Are these higher or lower? Are these a high number or a low number? I'm going to give this a high number. I give it a high number. I mean, based on nothing else at all. I haven't seen anything about these. I don't know what they are, but they kind of look, I would say they kind of look similar, right? They've got lines going to the right. They're light and dark, and they're almost the same, but you can tell they're not exactly the same. So I would give this a 6 or a 7. And I would give this a lower number. And what would you base that lower number on? Suggestions here.
The direction of the lines.
The direction of the lines. You might also notice the thinness and thickness of the lines. These are just visual versions, by the way, of the sine waves that we just heard. So if you took those waves that we heard to make the tone and imagine what waves look like, down, and then imagine looking down on the waves. So at the top of the wave is light and the trough in the wave is dark. That's what it would look like. So it's just a visual version of those sounds that you heard. They have up and down waves and they tilt a little bit. Eventually, you'd probably get pretty good at this task and you would all produce, and by good, I mean we would all produce pretty much the same responses. We would all agree on what's similar and we would disagree on what's and we would agree on what's dissimilar, and we would use the two features that we can describe separately. What about these two? Are these high or low? High number or low number? What would you give?
Low?
I'm going to give these kind of a lowish number. They're not very similar, but I don't really know. Are these, is this higher or lower? Are these more similar or less similar than what you saw before? Anybody have a guess? I don't know what the answer is, so you guess. Let's guess more similar. There's only two answers, more or less. How about these? Is this higher or lower than what you saw before? So here's one pair. Let's say we give this a 3. Would you give this higher or lower than a 3? I give this higher. These look more similar. How about these? I don't even know anymore because they all kind of look the same. So one points I want to make, now this I can definitely say these are not similar. I'm really confident here, right? This is a very low number. What do you notice that's different about this set of objects that the first two objects didn't have?
No distinctive features.
There's no distinctive features. There's nothing that we can label. We can definitely see that they change. I mean, that's not in dispute. You can definitely see these can change. And if you had enough chances to do this, we would probably all agree on similarity. We would probably all rate the things that are closer in physical space as being more similar, even if we couldn't describe it. But there is something different about these, and that is that, as you said, they don't have distinctive features. The way a psychologist would describe this is that the features are not separable. These are non-separable features. In the previous two stimuli, the fish and the sine wave gratings, those features were perceptually separable. We could see the grating fineness, like the spatial frequency of the light and dark bands, and we could see the tilt. Those two things were completely independent of each other. The features here, which might be something like hue, brightness, contrast, etc., different sort of aspects of color, are not perceptually separable. If you change one, it changes your experience of the entire shape. We can't really perceive a change in brightness separate from a change in the overall. So these are perceptually integral. These are what are known as integral dimensions, and in the previous it was known as perceptual dimensions. That's one case where the calculation of similarity seems to diverge. You can sometimes get at this a little bit different with and we'll come back to what that means in just a minute. You can sometimes get at this distinction a little bit differently by asking participants to make a forced choice decision. So this is the second way to measure similarity. Talking about ratings, Forced choice just means I give you a standard and then I ask you to pick which one of two it's more like. That's a little bit easier for a lot of people to do because you only have one decision to make. You don't have to assign a value. You just say, well, the one on the left is more similar to the target. Sorting is another way to ask people about their perception of similarity. We can ask you to sort. Sorting tends to be a little bit easier to do for things that are perceptually integral. Or if they're perceptually separable, we tend to use a single feature when we sort things. So we sort the light things and the dark things, perhaps, maybe into groups. That would be the easiest way to sort these objects. You kind of see this distinction in sorting in a way that you maybe don't see the distinction in ratings. But presumably they all tap into our same metric. These are all just different ways to assess similarity. Okay, I want to now take a break. This is the perfect time to take a break. And I want to take what we talked about in the first half. The idea that we can do ratings tasks, that we can do sorting tasks, forced choice tasks. And I want you to remember the distinction between features that are perceptually separable and features that are not perceptually integral. And that's going to become an important part of this first theory or model of similarity, which is a geometric model. Okay, 10:36. Let's take about a 10, 12-minute break. And when we're all back here, we'll just continue. All right, see you in a bit.
Do sometimes.
All right, I think we're all back now. Let's continue. My goal here to finish this lecture at 12:10, if at all possible. It's important to set goals for yourself and to try to achieve those goals and to not be too hard on yourself if you fail to achieve them. So if we finish at 12:15, I will not be hard on myself. All right, we finished talking about ways to assess similarity. Let's talk about 4 different models of similarity. We'll go through the first 2 in more detail, and then the second 2, a little less detail, and then we'll sort of have some follow-up questions, a little bit of review, and I'll remind you again that the quiz is next week. So 4 models: geometric model, contrast model, alignment model, and the transformational model. They are all different ways in which we can describe the similarity process. Now remember, I said similarity is a domain general construct, but that doesn't mean that we have a model that explains it yet. So these are each different ways to explain how humans seem to use similarity in their judgments and decisions. Most of these models account for a lot of how we judge similarity, but none of these models accounts for everything. So we're going to spend most of our time on the geometric model because the geometric model is the one that's the closest to this physical kind of similarity that we were talking about, with features and perceptual features grounded in physical reality. And then we'll talk about some of the shortcomings with this geometric model and how those shortcomings of the geometric model lead to some of these other alternatives, if that makes sense. So in this geometric model, we're going to make a couple of assumptions. First, we just assume that similarity is represented in a psychological space. Think of psychological space as being an analog or a metaphor or a manifestation of physical space. So psychological space shares aspects with physical space, except in physical space, we talk about distance. Real, actual, measurable distance. I am physically closer to this chair than I am to that chair. It takes me longer to walk to that chair than it takes me to walk to this chair. So there's a physical distance. In similarity space, psychological space, similarity is the inverse of a psychological distance. The closer things are in psychological space, the more similar they are. the more likely they are to be activated in a spreading activation. The more likely they are to be activated when you use a memory or a representation to make a judgment or a decision or an inference. So similarity is the inverse of psychological distance, and psychological distance is analogous to physical distance. So let's think about this similarity ratings task when people rate the similarity of one object to another. So we choose a number 1 to 7 to decide what this is going to be. We choose a number 1 through 7, and we choose a number. And what we could imagine that we're doing, and what the model would describe that you are doing. So this is a mathematical model that describes the behaviors and the computations that you might go through, your mind would go through when it makes a decision to choose which number, 1, 2, 3, 4, 5, 6, or 7, to assign to those stimuli. I'm not going to ask you on an exam to use this equation to make a similarity determination, but I want to use the equation because it's a good way to explain the process. This equation stands in for a psychological process. And what we want to say is the distance between object 1 and object I and object A, so the J, the distance between two objects, the psychological distance, can be calculated by comparing all of the features. So in other words, you sum, that's the summation sign, object across each individual dimension K, and take the distance between the other object across each individual feature K. A subtraction means that if those objects are the same, if the features are the same, so in this case they have the same tail, the subtraction between one thing and the other thing would give you a distance of 0, meaning that they're not distant, meaning that they're highly similar because they're not distant. They are the same feature. If they mismatch, in this case there's only 2 values of things like the fish lips, then they would be a number greater than 0. In this case, let's just say it's the number 1. Does that make sense to everybody? So you're just comparing, and this is what we said you would do anyway. You would look at all the features, you would make a comparison, and you would just add them up. All this equation is doing is describing it mathematically, that I look at these 2 objects, or I think about those 2 objects from memory, either way, and I make a comparison by looking at all of the features and just adding up the distance or adding up the similarity. In a geometric model, we might then say, so this equation explains how the mind would calculate similarity between objects by relating psychological similarity to the process of calculating the distance between points in multidimensional space. There is one thing I do want to call attention to, though, is this exponent r. So 1 over r and r. And the r in this case refers to 2 different metrics that you might use when you're calculating this overall distance. So I can just count the features up. I can say that these things share 3 out of 5 features, and that makes them more similar than not. But what if I can't count the features? What if they are integral features? How am I going to do that? Well, I can still do it because I can still make those assessments. I can still look at the 2 objects and come up with some kind of sense about how similar they are, but I don't exactly know what the dimensions are. So this exponent assumes that you've got 2 different ways, and this helps us to put this into perspective. The exponent r corresponds to the mental use of what's known as Euclidean space, or the mental use of city block space. How many of you are familiar with the terms Euclidean distance and city block distance? So it might come up, I have no idea what scenario this would come up in real life, but maybe it did come up at some point in real life, Euclidean distance and city block distance. But here's how it might. Let's assume that you are in the upper west side. This is Central Park in New York City. If you've ever been to Manhattan, it's very grid-like, right? The streets are very grid-like. So you can sort of imagine a city block being exactly a block. In this case, it's kind of a rectangle. You're here and you need to get here. There are 2 ways, obviously, that you could imagine this distance being calculated. You could calculate the actual distance that you need to walk, which is if you're using Google Maps or Apple Maps and you say, how do I get to this address and then you select the little guy for walking, it gives you little dots. And what does it do? It doesn't do this. This would be your city block. This would be your Euclidean distance. It does not calculate the straight line distance. The shortest distance between any 2 points is a straight line. Sure, but you can't get there. You're not going to go that way, right? That's a Euclidean distance. It's the hypotenuse of this particular right triangle in two-dimensional space. And you all know what a hypotenuse of a right triangle is. It is this straight line between these 2 points. That's not how Google Maps is going to tell you to walk. Google Maps is going to tell you to do this. It's going to tell you to walk a certain number of meters or feet this way, and then it's going to tell you to turn right and walk a certain number of meters or feet this way. Which one of those two is longer? In the universe of physics, which one of those two is longer? The second one, the city block one, is longer. If you had the ability to walk the straight line, you would get there faster. But obviously you don't have that ability to walk that straight line. So these are two ways to calculate distance. Now, based on what you know about those kinds of objects we were talking about, the fish and the sine wave gratings and the colors, what kind of similarity do you think each one would use? So if you're using this, if you're using these stimuli to make a similarity distinction, are you likely relying on city block space, or are you likely relying on Euclidean space to calculate the distance?
First two would be city block, and the other one would be.
I think you're right about that. So if you didn't hear the answer, the first one is city block space. And that turns out to be the case. When people make similarity distinctions, similarity judgments, their judgments are fit well by the city block model because you count up individual features, just like you would count up individual streets to walk on when you're walking to that particular place, right? So it's not a Euclidean distance. It's the slightly longer way. When people make judgments about these, they usually use, again, city block space because the dimensions are perceptually separable, just like streets are separable. But when you have to make judgments about objects like this, the Euclidean model is a better model to describe your judgments. It's the same equation. It's the same underlying idea that you compare the distance in psychological space between two objects and you assign a value of similarity. But you calculate it in a slightly different way. You calculate it according to this Euclidean distance rather than the city block. This turns out to have some interesting aspects to it, which we're going to talk about when we talk about some of the shortcomings of this particular model. But for now, keep in mind that people can use both types of metrics. We can perceive the similarity of objects in psychological space in a Euclidean space, and we can perceive the distance in psychological space according to city block space. And city block seems to be more applicable to cases when dimensions are perceptually separable. Does that seem straightforward? Perfect example, by the way, of a type of question that I might use on a multiple choice or even a short answer. What kind of, if you have to compare the distance between this shape and this shape, would this be city block space or Euclidean space? Kind of a true or false type of question almost. It's just two choices. So think about this as something that's an obvious type of question that I might ask. All of these objects, so if you ask people to make lots and lots of similarity judgments, you ask them to look at shapes or look at objects or look at things or think about things or think about concepts, and you ask them to say, how alike are these? How alike are these? How alike are these? What you tend to get is a representation of the psychological space of a whole bunch of concepts. So if we were to ask people, I ask you, to consider the goose and the duck, are they highly similar or not highly similar? Most people would give a high rating. They're highly similar. A goose and a duck, although the goose has specific aspects of aggression that ducks don't have, we kind of lump them together sort of in the same general category. And if you think about a blue jay, it's not really very much like a goose at all. They're all birds, but some of them are closer, some of them are more similar. And if I were to ask all of you to rate all of these different objects pairwise, goose with duck, goose with chicken, goose with goose, goose with animal, and so on, we might all come to agree that our psychological space kind of looks like this, that there is a dimension of domesticness that might vary across different animals, such that geese and ducks and chickens kind of seem a little bit domestic. We see them. Pigeons might seem kind of domestic, but not as much. Whereas hawks and eagles and blue jays don't seem domestic. Even if they're in your backyard, you don't think of a hawk as being a domestic bird the way you might think of a duck or a chicken or a goose as being a little bit more domestic. And maybe you have a size dimension. Maybe this isn't domesticness. Maybe it's more like more wild, less wild, which I guess is another way of saying domesticity. It's just a label that we give to these dimensions. Size, we got big things and small things. And then we could probably characterize the entire conceptual psychological space of your bird concept along two different dimensions, where we think about things in terms of their wildness and in terms of their size. Color probably doesn't make any difference at all. These are two important dimensions when it comes to conceptualizing how we think about birds. So this would be our psychological space for the bird concept. Does that make sense? This is a psychological space. And if I think about geese, I'm more likely to think about ducks because it's a closer concept. I'm less likely to think about a cardinal. In fact, if I think about a goose, I never think about a cardinal. It's just not something that comes to mind because it's way over here in a different region of psychological space. But if I'm thinking about a cardinal, sparrow, robin, and blue jay are close by because they occupy the same area of semantic, perceptual, psychological space. Does that make sense to everybody? Great. Paper that I've been really interested in, and I'll tell you why in a few minutes, is a paper from Robert Nosofsky. So I talk about this in the textbook a little bit. So let me talk about this paper a bit. What Rob Nosofsky is interested in, he's a researcher at Indiana University. And most of his area of research is in psychological space, similarity, concepts, and categories. And he was interested in how people learn about complex natural science categories. How many of you have taken like the first year geology course, rocks, something? It's like rocks in space or so. I don't even know what it's called. You know what I'm talking about. It's like first year rocks course. Anybody taken this course? Nobody's taken, what's the name?
Took it, it's called Earth Rocks.
Earth rocks, that's what it was. And it's literally about Earth rocks, not space rocks. It's about Earth rocks. What do you know about Earth rocks, right? I mean, there are different kinds of rocks. How many of you know the three different kinds of rocks that there are? Sedimentary, igneous, and metamorphic, right? So there's three kinds of rocks. How many of you know what those kinds of rocks mean?
Like igneous comes from like sedimentary. Shit like stacks on each other, like flattened and metamorphic.
Combination of both, and so there's some change there. So if you didn't hear igneous rocks, those are volcanic in nature, right? Those come from the earth, they're created in fire. So these are volcanic rocks. Sedimentary rocks are rocks that are formed over long periods of time from sediments, things that stack up under pressure. And metamorphic rocks are rocks that have undergone a change that might have once been igneous in nature, but through high pressure or some other process have changed into something else. So there are three kinds of rocks. These should be similar in the way that Jill and Priscilla were similar because they are caused by the same thing. Igneous rocks are all caused by volcanoes, right? They're caused by volcanic action. Sedimentary rocks are caused by layers of sediments. So there's an underlying causal factor that links those things together. But if you took earth rocks, or if anybody has ever thought about this beyond just the little bit that we're going to talk about it today, these rocks don't look at all like each other. There isn't like one look to sedimentary rocks that would let you know, well, these are all clearly sedimentary rocks. There's a lot of other features. Just like Priscilla and Jill, they can differ a lot in how they look, even if the causal factors are the same. So what Nosofsky and his colleagues were interested in were two things. First of all, do people know this? First year geology students, how do they perceive the similarity among all of these kinds of rocks? Do they have any ability to tell the difference between igneous rocks and sedimentary rocks when they're asked to make similarity judgments? And then secondarily, Are people able to learn these distinctions? I'll tell you a little bit about some research that one of my postdocs is doing that has determined that experts behave differently and novices do in exactly this kind of task. So I'll summarize the stimulus and procedure. People literally looked at hundreds of pictures of pairs of rocks and rated them for how similar the pairs were. So hundreds of trials. In fact, it was 435 unique pairs were shown once in a unique random order for each individual subject. You're just looking at rocks and you're saying, are these similar or not? It would be a very painfully boring task to do. But people can do it and they agree to a large degree on what is similar and what is not. And so what they had were types, different kinds of rocks based on formation, but not necessarily in appearance. Remember the example of Emery-Dreifuss muscular dystrophy from the beginning of lecture. Same cause, different appearance. Igneous rocks, metamorphic rocks, and sedimentary rocks, and here are all the different kinds. Basalt, granite, dolomite, and so on. These are all different kinds of rocks of those types. So we all agree geologically igneous rocks have the same cause, but they are different kinds of rocks. And they look different. You can see this a lot more clearly on your individual slide that you can see here. But what you see is, let me see if I can point to it a little bit closer. So here's a sedimentary rock. It's a type of sandstone. And it looks a little bit like pumice, which is an igneous type of rock. So clearly, when participants are rating the similarity, they're using things like the saturation, which is sort of a color density, or the organization, meaning that some things are chunky and some things are smooth. The grain size, maybe the size of the chunks, and the lightness. So that when people rate the similarity, they rate them across these 4 dimensions. Or we can look at it and consolidate maybe the grain size and the organization into 3-dimensional space. Rocks that vary in terms of lightness. There are light rocks and dark rocks. So you saw some light rocks over here, and you saw some dark rocks. There are saturation rocks, rocks that are all one color versus rocks that seem to be a mix of colors. And there are grain size, rocks that are really smooth, like in this case, I think it's obsidian. Has anybody ever seen obsidian? It's like a shiny black rock. So it's dark, it's shiny, and it's very uniform, as opposed to something like granites. If you have like a chunky granite countertop, you're going to see that it has lots of different variegation. And people were sensitive to that, and that's what they base their decisions on. One thing you can also notice is that that's all novices, which is to say introductory earth rocks students, have access to. They can perceive the grain size, the lightness, and the saturation, and these different shapes here correspond to igneous rocks, which are these spheres, cubes, which correspond to the metamorphic rocks, and diamonds, which correspond to the sedimentary rocks. And what you probably notice is there's absolutely nothing there. Novices, students who are learning about rocks in an introductory geology class, have absolutely no idea how to place these rocks into their correct categories. All they can do is pay attention to the features. And these seem to be features which are mostly separable, but not quite. And so what they're doing is behaving accordingly. They're paying attention to the things that they can pay attention to, and they're unable to sort these or make similarity judgments that suggest that they understand this difference based on what how these rocks are formed. I don't have the slides here. I wish I had access to them because they're still under development. My postdoc has asked a group of about 40 geologists to do exactly the same task. First of all, we replicated Nosovsky's work really well. We used exactly the same rocks. We asked a whole group of undergrads to do the task, and they came up with almost exactly the same sort. It's a very high correlation, like 85, an R of 85. So it's a very strong correlation between our results 10 years later and Nosovsky's results. So this result holds up really well. We then asked experts to do the same classification, and they show access to the underlying causal features. So experts don't look like this. Experts put igneous rocks with igneous rocks, and they put metamorphic rocks with metamorphic rocks, and they see sedimentary rocks as being more similar to each other because they're sedimentary. They still notice lightness, grain size, and saturation, so it's not like they don't pay attention to it, but they don't have this intermixed sort. They do tend to group things based really nicely on these particular causal features, suggesting that enough experience, just like Priscilla had her own, or Jill had her own individual experience with that particular type of muscular dystrophy, could look beyond the surface features to see the causal features. Yes.
This just reminds me of k-means clustering.
Yes, that's exactly what we used to do the analysis. It's a k-means clustering, which is a way to look at psychological space and similarity making. That's a really good insight. We have this manuscript under revision, under preparation. It hasn't been submitted yet. But it's a really interesting paper because it suggests that novices and experts differ along the way we expected them to.
How many dimensions can you use in a scalable solution?
That's a great question. So the question is, how many dimensions can you use? Well, there's a couple of different ways to decide that. Typically, you use something, essentially you use a plot that helps you determine how much more variance is accounted for by introducing new dimensions. And you tend to cut off the number of new dimensions when plot flat. So there is a little bit of judgment there. More dimensions gives you more explanatory power, but there's a point at which adding new dimensions doesn't increase the fit of the model. That tends to be what you use. So in this case, Nosowski was using both 4 and 3. 3 is really good in cases like this because it's easy to visualize. Anything beyond 3 dimensions requires multiple plots, which makes it harder to think across. Does that make sense? That's a good question. Does that seem straightforward to everybody? So this suggests that we're all living in a geometric model when we're novices. But when we're experts, you maybe aren't living in a geometric model. And that suggests that the more you know about something, the less bound to perception that you actually are. Jill wasn't doing that. Clearly, she wasn't bound to perception because although it was perception that gave her the clue, it wasn't perceptual similarity. And experts in this case are not bound to perception. They can notice it, but it isn't what they're using to make their decisions. So let's talk about these core assumptions of this geometric model and how they can be violated, sometimes by people with individual experience like experts, but sometimes just by knowing something. These are all knowledge-based assumptions. They are minimality, symmetry, and triangle inequality. The first two are really straightforward. The third one takes a little bit more explanation. Minimality just means that things should be most like themselves. Because in a physical world, whether it's 2 or 3 or n-dimensional space, a point is always closest to itself. I am closer to myself than I am to anyone else. That's kind of obvious, right? So if you're thinking about similarity of perception or objects or ideas as existing in a psychological space that is the same as a physical space, one thing should always be more like itself than anything else. There shouldn't be anything that interferes with self-similarity. You should be able to rate the similarity or judge something as being most like itself. It's occasionally, in some circumstances, if the perceptual characteristics are right, it can be violated a little bit. In other words, it means that the perceptual characteristics of something make it hard to make a similarity judgment that's completely universally minimal. These are 2 ways to express it. Similarity of A to A is always less than the similarity of A to B, or the distance between I and I is going to be less than the distance between I and J. Does that make sense to everybody? So a couple of quick studies I'll show you just on the next slide. Essentially, if you flash objects, letters, for example, on the screen quickly enough, people should always be identifying same letters faster than different letters. But when they make errors that suggest that there are competitors based on close similarity. So if I were to flash this letter and then flash this letter, you would say those are different. And if I were to flash this letter and ask you to name it and then compare with this letter, you might have a confusion. It depends on how similar those letters are. This one should be easy for most of us. It's an L. If I ask you to identify that, it should be easily identified as an H. This one might be a little bit more challenging. What you would find is that that one might be occasionally misidentified as an H, occasionally misidentified as a letter A, because it shares a lot of features. If you're doing this fast, and if you're doing it with a lot of different objects that look like each other, you're going to make predictable errors. All this is suggesting is that sometimes our perceptual system gets confused. And it gets confused in a way that would make it look like we're not adhering to this minimality assumption. Does that seem straightforward enough? It's not a clear it doesn't suggest that the geometric model is wrong, but it suggests that when we make mistakes, they seem to be based on this larger region of perceptual space. And you can see all the objects here. So a study, letter M in this case, is recognized as an H as often as it is as an N. So we make errors and we make consistent errors. This isn't just about similarity and overlap. It has to do with the amount of information that's present in each individual display. And the reason this is a problem for minimality is that L also overlaps with lots of other features in letter displays, but people don't make errors on L. There's something about this particular configuration of pixels that lets L be identified really quickly and rarely confused, but M is identified more slowly and more frequently confused. So it isn't the case that for letter identification or symbol identification, things are perfectly minimal. There's always going to be some interference. A little bit more complicated is the idea of symmetry. Symmetry suggests that if we know something about one domain, we tend to prioritize it. If we know more things about one object, we tend to think of it as the more important object. It's the thing you compare something to, rather than the thing you're doing the comparison. It's the standard that you compare something to rather than the comparison object. So according to the symmetry assumption, dissimilarity should not be affected by the ordering of items because the distance from point A to point B is equal to the distance point B to point A. So the distance from me to that clock is the same as the distance from the clock to me, right? It doesn't change any. It shouldn't change any. So if physical space and psychological space are the same thing, then it shouldn't matter which one I ask about first. If I ask you to compare the difference between A and B, it should be the same as comparing the distance between B and A. But you can probably already figure out that that's not going to always be the case. If I know something more about one of those two things, it's going to change the ordering. Let me explain what this means. Prominent, but the non-prominent item, the thing I don't know as much about, is judged to be more similar to a prominent item than vice versa. In other words, people judge their friends to be more similar to themselves than they are to their friends. Your friends are like you more than you are like your friends. Does that make sense? You might think of your best friends. Think of your group of friends. You can probably imagine yourself, and not in an egocentric way, probably imagine yourself as the center of your group of friends, because how many friend groups do you have? More than one? I mean, you could have 0 friend groups like me. But suppose you have more than one friend group. You've got a friend group and you got a friend group and you think, I'm the glue that holds these groups together. But you know what? Those groups are not thinking the same thing about you. And you're not thinking, I am just like all of these other people. You tend to think of yourself as the middle of your friend group. And that's been reliably shown. People do judge themselves as being more similar. They judge the friends to be more similar to themselves. They're like me. That's why I'm at the center of all these friend groups. But I'm not like them. I have differences, right? I'm unique. I'm an individual. I know more about myself. Rare colors are judged to be more similar to common colors than common colors are to rare colors. If I know something about one of these domains, if it's common or if it's me, I'm more likely to think that things are similar to me or that they're more likely to be similar to the thing that's more common. Here's the most classic example, the most famous example. I talk about this in the textbook. This is from Amos Tversky's work in 1977. Tversky is one of the founders of the science of similarity. I've got a little bit of a clarifier here because the term specifically Red China, which is the term that Tversky used, meant communist China. It's still communist China, but Red China was a common term to use in sort of the Cold War era in the US and Canada. So in this particular case, similarity is asymmetric. It is not symmetrical. In one of Tversky's example, North Korea was judged to be more similar to communist China than communist China was similar to North Korea. In this sense, the Chinese government at the time, in the 1970s, under Chairman Mao, was perceived to be closely aligned with the Soviet Union of the time, a specific kind of communism. And North Korea was an example of that as well. So most North Americans would have thought, okay, well, I know what North Korea is all about. It's a communist government. It's a particular type of communist government. China is like that too, but North Korea is like China in that regard. China is not like North Korea in that regard. They share the same thing. We're rating them on the same thing, which is their geopolitical stance. But participants, when asked, don't see it as symmetrical. They see North Korea as being like China. They don't see China as being like North Korea in this particular sense. Does that make sense to us all? Some things are symmetrical. I was just using the washroom. There's nothing similar about me using the washroom. You've probably seen the sign that says, toilets are not garbage cans. Well, no, they're not, but I would say that garbage cans are not toilets. That one is pretty symmetrical. Don't use the garbage can as a toilet and don't use the toilet as a garbage can. Totally different things, but I think that's kind of a symmetrical example in that particular case. So symmetry does work sometimes, but it doesn't work all of the time. Does that make sense to everyone? Okay, last example, and this is where, remember, this, the importance of separable features comes back here. The distance and dissimilarity between 2 points A and B can't be more than the distance between A and a third point C plus the distance between C and B. If you're lost, let me visualize this for you because it helps to visualize. A straight line connecting 2 points is the shortest path, is an easier way to say that. So triangle inequality means that in a larger psychological space, we often have things that are connected along a straight horizontal and vertical, and we sometimes have things that are connected along a diagonal. Now that diagonal is longer than two things in either one of those two, horizontal and vertical, but it's not as long as the two of them sum together. Does that make sense? That's your hypotenuse of a right triangle. Let's visualize this and you'll see how ratings sometimes differ. So let's start with a simple example and then I'll start with a social category example and we'll see how this plays out. Imagine a psychological space that exists of circles of different sizes and different colors. We've got a size dimension with little things and big things, and we've got a color dimension with red things and white things and less sort of in between things. Does this make sense? So you can imagine other shapes that fill in here. I've just depicted 9, but imagine there's lots of other sizes in there. There's things in between here, there's colors in between here, but this is the universe that we're talking about. There's a universe that has 2 dimensions, size and color. And then we ask participants, I ask you, to rate the pairwise similarity of all of the objects in the space. In other words, maybe you rate the similarity of object A to object D. You rate the similarity of object A to object B, of object A to object C, and so on. So I'm going to ask you to rate the similarity of these objects. And what we're going to be concerned with in this particular case are these 4 objects, A, B, C, and D. If the world of psychological similarity in psychological space is exactly the same as 2-dimensional physical space, the similarity rating between A and D, right, would be less than the similarity rating between A and B and C combined. This line here, A, B, C, is going to be longer than A and D. This line here, though, ABC, is going to be shorter than A and D plus C and D. Does that make sense to everybody geometrically? You could sort of run it as basic, like grade 4 geometry. So geometrically, I think you could probably all see where this triangle inequality comes out. This geometric model predicts that A and B should be less than A and D, for example. This match here, A and D, is going to be a longer line than the line between A and B. Does that make sense to everyone? But it's not going to, but you can see it right there. That's what it is in physical space. But in ratings, similarity ratings, participants won't give you that answer. Participants will rate A and D as being more similar. That'll be it'll almost as if they have condensed or squashed the psychological space only when they're making that judgment. But people display empirically demonstrated violations of this triangle inequality. Here's the inequality right here. This line is shorter than this line, such that A and D is less than A and B. The reason they do that, the reason that people seem to find that as a less distance, in other words, more similar, is because of a dimensional match. These are perceptually separable dimensions. And in cases where there are dimensions that you can perceive separately, and you can name separately, a lot of us give extra priority or extra weight to a dimensional. Another way of saying that is the dimensional match enhances the perceived similarity. This is the same exact size. And although they're completely different colors, there's something about them being the same size that makes their similarity stronger. It makes the distance between them seem less. It's as if when there's a dimensional match, the two-dimensional psychological space gets squashed in. Does that seem sensible? So this is an effect of knowledge. You know something, you know these are the same, and you think, well, they are the same shape, they're the same size, they must be more similar. It isn't just that in this giant range of psychological space of circles of different sizes and different colors that they happen to be in a particular positions of psychological space, it's that they're the same size. So of course I'm going to say they're really similar. I don't care that they're different colors. In fact, that means nothing to me. What's important to me is they're the same size, and I'm going to give that a really high rating. And that seems to be how people act in a lot of cases. Once there's a dimensional match, it heightens the similarity. That's a little abstract. About 2 years ago when I was teaching this course, somebody said, are there any real world examples of such a case? And I thought for a minute, I don't know about this. I've been teaching about this from an abstract point, circles and lines. What's something real world? And here's an example that we came up with in class 2 years ago. Let me just point out that my decision to record my lectures and make them available as videos proved really useful because I had to go back to the video to remember the example the next year. I was like, wait a minute, somebody gave me a good example and I said I was going to remember it. I didn't. What did I say? Here's what we came up with. Consider social and occupational categories. Let's suppose we have young and old people. People 22, which is closer to your age, and people 62, which I'm not yet, but is closer to my age. So we got youngs and olds. That's a dimension, right? And we would think that regardless of your trade or your profession, you would like to think that youngs are more like each other, right? And regardless of what line of work they're in, you'd probably put all the olds together in a category. You could say it's all those old people, right? It's all the young people and all the old people. And we would tend to minimize any of that difference. We would see young people as young people and old people as old people. And then consider the difference between trades like plumbing, electrician, mechanic, carpenter, and professions like accountant, lawyer, etc. So those are two different dimensions. So we've got young accountants and young plumbers and old accountants and old plumbers. Does that make sense to everyone? So imagine these are Google image searches. These are not AI generated. This guy actually posed for this picture. Here is our young plumber, and here is our old plumber with a much bigger wrench. So we could imagine those as being some coordinates of psychological space. And there's other plumbers somewhere in there, right? And the same thing with professions. Here is a young accountant, and here is an older accountant. I literally Googled old accountant, and that's what it gave me. And I Googled young accountant, and that's what it gave me. So these are trades and these are professions. And then we might ask people, not just based on the physical characteristics of that particular picture, what's most similar? And then suppose we ask about the person in the middle. Here is a middle-aged, well, he's a manager. He's a project manager for a construction company. Is he a trade or is he a profession? I don't know. He's kind of a little bit of both, because here he is clearly on a work site. So he's kind of like a trade, but here he is in front of his laptop, clearly doing some business work. So he's doing some business development work. So probably has some accounting skills. So maybe he's a project manager for a development company and not one of the subcontractors. If I'm then asked to say, how similar is this guy to this guy versus this guy to this guy, what's the decision that I'm going to make? Well, if I care about trades and I say, well, he's a plumber. Yes, he's a young plumber, but he's more like this guy because they're both going to be hired as plumbers. And that might shrink the psychological distance between them. Yes, one's very old and one's very young, but when we're thinking about them as being plumbers, we say, well, they're both plumbers. They're much more alike. And they're closer to each other than this guy is to this guy, even though he's closer in age and still sort of in the same line of work. So I think this example kind of works well. And you could probably imagine other cases like this, examples where as soon as you know something about somebody, you put them into a category. And once you put them into a category, it shrinks the psychological space. Knowing what somebody is makes them more like the other people that are in that concept. And that's the main point of this psychological effect of this triangle inequality. And that's really the same thing that's going on with symmetry. Once you know something about somebody, it makes them more similar to those other things, to those other people, or to those other objects. Does that seem straightforward to everybody? So we got 3 assumptions, and I've got 3 ways in which they're violated. I always have a question on the midterm that says some version of what are the 3 assumptions and how are they violated? Give me an example of how the symmetry assumption is shown to be violated by human judgment or empirical decisions. And so you might recall the North Korea, China example. I might ask for an example of the triangle inequality, and you might recall the circle example or the plumber example. So that would be a good example of the type of question that might involve a 2-step answer. What is it, and how do people, what does it predict about people's behavior, and how does their behavior differ from the prediction? Does that seem clear? I won't do this for every class, but I do find that at the beginning of the course, it can be helpful to sort of give you some idea of how I might assess these things and how I might ask about them on a midterm or a final exam. So Amos Tversky, who came up with a lot of these examples, came up with an alternative model called the contrast model. And this doesn't mean that the geometric model is wrong. It just means that it doesn't capture everything about human judgment. Humans do seem to behave as if they're living in a geometrical model, but not all the time. The more you know about something, the less geometrical it seems, because you know stuff that can't be measured geometrically. And Tversky says, we might want to model this in a different way. Let's call it a contrast model. And that means that not only do you assess similarity by looking what things have in common, which is what our geometric model does. It says the similarity between object A and object B is given by the overlap between A and B. So the union of vector A and vector B. So here's 2 concepts. And what do they have in common? Do they have things in common by features or perceptions or behaviors or functions? Whatever it is, whatever they have in common increases the amount of similarity. The more things they share, the more similar they are. Then, after I've done that, I have to take away from it things that are distinctive to A and things that are distinctive to B. So if 2 things are similar because they share features, the degree to which A has unique features, features that B doesn't have at all, that I can't even compare to B, that's going to take away from that shared similarity. And if B has features that A doesn't have, that's also going to take away from it. But these things aren't going to necessarily be equal to each other. I might not know anything about B, so it makes it easier to calculate what's unique about A and harder to calculate what's unique about B. If I only know about object A, I can say these are things unique to A because I see them in A, but I don't know much about B. So I don't know all of the features that B might have that make it unique from A. And that predicts asymmetric similarity. The contrast model predicts asymmetric similarity because A is not constrained to equal B. I might know a lot about object A and very little about object B, or object A just might have a lot of facts about it, a lot of features, and object B might have few. They don't have to be equal. And so the function A minus B, the distinctive features of A, might not equal the function of B minus A. And that predicts asymmetrical similarity judgments. If I know more about A and less about B, then the comparison differs depending on when I ask you to compare something to A versus to B. Does that kind of make sense? North Korea, in the example from Tversky, can be seen as predicted to be more similar to Red China than vice versa if Red China has more salient distinctive features than North Korea. 1977, most people would understand a lot more about China. China's a bigger country. In terms of geopolitical, I mean, that's true now, even more so. In terms of geopolitical impact, China has a lot more geopolitical impact on the world than North Korea does. But even in 1977, kind of at the height of what's known as the Cold War, when there was sort of an ideological difference between the spheres of influence controlled by the Soviet Union and the spheres of influence controlled maybe by the United States, Western Europe, and so on, which kind of seems like what we have now. North Korea would have been a smaller concept. China would have been a much bigger concept. It would have loomed larger in people's minds. So the comparison is asymmetric. The contrast model predicts this pretty well. Okay, does that seem pretty straightforward? We've got 3 more models. I'm going to talk about some problems with both the featural aspects of geometric models and contrast models. And we're going to hit 2 other models, and then we're just about done. Do you have the stamina to make it to 12 o'clock, 12:10? We're on track. Okay. What are some problems with this featural account? Before I even go on, what would be some problems with a featural account of similarity? What do you think would be a big problem to explain human behavior by just paying attention to features? Any thoughts? You were thinking, yes.
Like different internal processes can have like the same outward response.
So different internal processes can have the same outward response. In other words, we might behave towards things similarly, even if we can't see that on the outside, and vice versa, I think is what you're saying, right? Okay, yeah.
Like that rock example, like they might go the same transformations, but then they might look like the features could be like completely different.
Might go the same transformations and the features might be different. So transformation might take an object, depending on how fast it transforms, might change the features differently. An even bigger issue that sort of, I think, addresses what both of you said, I think it does, is how do we even know what features are? We're talking about perceptual features, but we already agreed that there are functional features, there are behavioral features. And for every feature that you can label, you can also assume that that object has lots of things that you don't see at all. There are features that you can't perceive. And if you can't perceive a feature, do you label that as non-existent or do you label it as not having that feature? Does that count as a feature? Does the fact that an apple is not orange a feature? Or is not orange just not relevant here? If you start counting not having a feature as a feature in and of itself, then you might run into the issue of having an infinite amount of features, which makes a featural account kind of challenging. In other words, how do we know what features matter? Let's think about how this works. First of all, feature selection is flexible and context specific. we can focus people's attention on individual features. That triangle inequality depends really a lot on whether or not people notice a dimensional match. But if you didn't notice the dimensional match, then you might not show that triangle inequality violation. So it's flexible and context specific. Here is an example of a forced choice task from an experiment from Doug Medine's lab. So we won't go into the details of this particular study, but just to focus on the objects themselves. Here's the target, and I'm asking you to choose which one of these two, A or B, are more similar to the target. Which one is more similar, A or B? Most people say B. B is more like T than A is like T. Would you agree with that? That A is less like, so B is like it, and why is B like it?
All the objects in that group are all, we don't have that pattern.
So there's an internal consistency. They all have the same pattern. That's kind of already sort of a high level feature to begin with, right? It's a configuration of shapes, the configuration of shapes that's all checkerboarded or no checkerboarded. And so having the same internal consistency of pattern is a feature. You probably didn't even think about that as a feature until you saw this and had to make the distinction. Medine also found that B was more different. If they asked people to make the judgment, which one of these two is more different, people also chose B, the same set. Now, why would B be more different?
Missing any of that.
It's got no checkerboard, so you would say it's more different. So what Medine found was that this set of shapes here, B, was simultaneously more similar and more different from the target, which raises some problems for any model that depends on feature. How can an object be the same and different at the same time? Unless you're in some sort of quantum universe, which I guess we are, if we're thinking about psychological space, something could be simultaneously more the same and more different. That's what Medine's work is suggesting. Here's another example, and then we'll get to why this is a problem. The potential features could be high in number or even infinite. So Medine is now showing in that previous case that depending on which features we select to pay attention to, we can have something be similar or different. Here's another example. Again, here is the target, and here are two forced choices from the same paper. The target is more like A. Why is the target more like A? What's our example for more like A? So if you choose A as the better match, why is A the better match in this case? Any guesses?
There's one square, whereas B had no.
There's at least one square. Different shape, different configuration, but it's a square. So you would say, okay, well, if I got to choose A or B, B looks nothing like the target. A at least has a square. So square is a feature that I can use. Now I take the same target and I compare it to A or B. Why would A be more like it? It's a black square, right? A is also more like it. Now, why is A more like it here than B? What would be the reason for A to also still be more similar?
The object on the left is filled in black instead of the object on the
Object on the left is filled in black. So now it's a configuration of colorings. In one case, we pay attention to the shape. In the next case, we pay attention to the shape and the color. In the next case, we pay attention to just the configuration of colored and non-colored spaces. So there's lots of different ways to analyze exactly the same types of features. And what Medine is suggesting is that we can't just rely on features. This is a problem for the contrast model, and it's a problem for the geometric model. In similarity, human similarity judgments have to depend on more than just feature comparisons, because feature comparisons alone will not explain people's judgments. And these judgments seem to suggest that we use something else. In some cases, we use our knowledge. In other cases, we flexibly adapt to individual features depending on the actual configuration of the things that we're being asked to consider. So let's do some more examples as we talk about some of these other models, but these are accounted for by a large class of similarity models or theories called alignment models. Mostly what I want to say about alignment models is that we take into account the overall configuration of objects and their relationship to other objects when we make similarity judgments, when we judge how things relate to other things. Simplest way to understand an alignment-based similarity is to think about the similarity of maybe the tallest person in a group. So in your friend group, you probably have a person who's the tallest person. Regardless of which friend group we're talking about. You got a friend group, you got the tallest person in your friend group. And although they might not be very tall, suppose you have a short friend group, and your friend group, the tallest person is only 5'8". They're still the tallest person in your friend group. And in fact, they've got something in common with the tallest person in a tall people friend group, right? If the tall people friend group has a tall person who is 6'4", and another person who is 5'8", that 5'8" person occupies a different space in two different friend groups. In one case, it's the tallest. In the other case, it's not. And so what we would think is that in an alignment-based model, we take into account not only the features of the object, but the features of the object in its context. And so if we ask people to rate all of these objects and think about them in context, when they're taking the target, they're more likely to make a relation match. Subjects who consider all of these objects will find that the target is more like the smallest item. People who don't see these objects as a whole group are more likely to make a direct size match. If you don't know about the friend groups, a person who's 5'8" would be matched with the other person who's 5'8". But if you say, pick the tallest people in my two friend groups, you pick the tallest person in this friend group who's 5'8". 5'8" person in this group might be the shortest one. They don't get to go in this new group of tallest people in your friend group. Does that make sense? So we can take that into account, even though it defies individual feature comparisons. This is a new kind of knowledge that doesn't seem to be accounted for by either a geometric model or a contrast model. We can use the geometric model and contrast model to make decisions about those objects, but in order to decide what comparisons to use, we've got to use something else. In this case, it's configural knowledge. So I say subjects who rated the similarity of all the sets, in other words, they considered all of the sets together, were more likely to use the relation match. Subjects who did not consider all of the sets chose the size match because it was the only thing that made sense in this case. Is that good? One final model, and then I'm going to use another example of flexibility, and then we'll do some quick review. The last model I want to talk about, I won't have as much to say about it, but you can read a little bit more in the textbook. The idea is transformation. And that's a fourth aspect of similarity that isn't captured by the other models. And that is that sometimes, so geometric model is just talking about features. Contrast model is talking about shared features and distinctive features. Alignment model is talking about features in relationship to other features. And the transformation model assumes that not only do we take into account features, but we take into account the degree to which features change over time or change over steps. The number of steps that it takes to change one feature into something else, more steps, less similar. So you can imagine things do transform. Water transforms into steam, and you can imagine steam, although it's not at all like water, is probably closer to water than some other kind of vapor. Maybe it's more like water than it otherwise would be because you know there is a transformation. Molecular structure might be the same. It's made of the same molecules, they're just in a different configuration. We might also ask children, and this is studies have been done with children have found that they can appreciate that there are real physical differences even though there are transformational similarities. So the standard monarch butterfly caterpillar. How many of you had to have one of these in your grade 4 classroom or something like that? It's a pretty common thing to do, right? To have a caterpillar and to watch them transform into monarch butterflies. And so we can ask naive and experienced participants, in other words, children who know about butterflies and children who don't know about butterflies, to make similarity judgments. If you know about butterflies, This is a good similarity match, right? Even though they don't look at all the same, you know these are the same species, right? This is Jill, this is Priscilla. There's something close there. These things, although they look the same, and they might look the same to a very simple image identifying artificial intelligence system, aren't the same species at all. There is still an overlap in the sense that this also comes from a caterpillar. But now we're just trying to look at the difference between this transformation. So the degree of transformation also affects similarity. Something that can transform into something else is more similar than things that cannot transform into something else. And the number of steps plays a role. You could also imagine, we used this slide at the beginning, looking at how tech devices have changed over time. And there are transformational similarities at play in the particular design choices that were made. Okay, last example sort of captures all of this together. And it also adds one other thing, and that is the idea of category variability. Sometimes variability affects your similarity judgments. Got at that a little bit when we talked about the objects in the Bedin study. Some of the objects all had this, they were either all white or all checkerboard. Suppose I ask you to think about a 3-inch round object. 3-inch round object's about this big. So this is a 3-inch round object. Consider a 3-inch round object, and in a forced choice task that you do in your mind, is it more similar to a quarter, which I don't have, but you know what a quarter looks like. You need them at no frills to get the card. Or a pizza, also round. Which is it more similar to? 3-inch round object, is it closer in similarity to the quarter or the pizza? How many would say quarter? I would. How many would say pizza? It's a defensible answer, but in terms of pure physical similarity, it's closer to the quarter, right? Because quarter is about 1 inch across. 3-inch round object is 3 times bigger than a quarter. A pizza is bigger than that. So which category does it belong to is a different answer. So if I ask you not to make a similarity judgment, but to make a judgment as to which category does it belong to. In other words, what is it? We can agree it's more like the quarter, but what is it? Is it more likely to be a pizza or to be a quarter? How many would say it's more likely to be a quarter? Nobody. How many would say it's more likely to be a pizza? You have to raise your hand at this point because you've ruled out all the other options. It is, and this is what subjects would say. In an experiment that Lance Rips described in the 1980s, suggested that for fixed categories, we can appreciate the high similarity. When people are asked to make a similarity judgment, they can appreciate that this is more similar. But when they're asked to make a category membership judgment, they can't do it. And there's a couple of reasons. One is that quarter has no variability. It's an essential category. Things are either quarters or they're not. Quarters have to be the same size. They have to be the same shape. They have to be made by the Royal Canadian Mint or the US government mint or whatever. You can't have a big quarter. There is no big quarter. There's no little quarter. There's just quarters. And they might vary in terms of some other characteristics, but they've got the same size and shape, and they have an essence to them as well because they have to have some legal backing. They're currency. Pizzas, on the other hand, are all over the place. They can be square, they can be round, they can be stuffed crust, they can be deep dish, they can be hand tossed, they can be thin crust, they can be sourdough, they can be big and they can be small, they can have different numbers of slices, and you can certainly imagine making a 3-inch round pizza. Maybe you would be disappointed to have one, but if you took an English muffin, put a little bit of ketchup on it, a slice of cheese, and put it in your toaster oven, you have made a very poor pizza. But it is still a pizza, right? It would still be on the fringes, the outer reaches of the pizza category. Not a good one, but a pizza nonetheless. And that's what Rips is suggesting, is that once we've accounted for all of the features and shared similarities and features that are distinctive and unique, there's still something else, and maybe it's something like category variability. Quarter has no variability. It accepts nothing else in it other than real quarters. And what Rips is also pointing out is that similarity does not always make sense to base our judgments on. We don't base our judgments on similarity all the time. We can all agree that it's more similar to the quarter, but we can't put it in the quarter category. And so this is a problem if we're assuming that a lot of other judgments like categorization, inference, memory depend on similarity, but Rips's work is showing, look, people can agree on similarity, but they don't use it. They use something else. They actually make the decision that is less similar and endorse it as the better category membership. This suggests there's a lot more flexibility that depends on knowledge. Categorization chose the variable categories. Similarity subjects chose the fixed category. Okay, one last question to think about before we go. It's 12:01, so we are right on track. And this is something I'm just curious about. Do you all, when you study for things, I haven't had to study for something for like 30 years. When you study for things, do you use similarity to group things together? Do you study the same topics or do you vary? How do you take advantage of similarity when you prepare for exams or when you study? Have you ever thought about this? Yeah.
Like, I think you probably use both. Like some things you need to remember because they're very similar, and some things you should remember because you know they're very different. Like kind of can see both sides to it.
So in much the same way that we saw some of those, maybe even the pizza quarter example, you say these things, I'll group these together because they are similar. I will group these things together because they're really not similar at all. And that means that they're similar because they're not similar in a weird way. Do you study with the same people? Like, do you tend to study with the same people even if it's different classes? Or do you always study with people who are in the same class? Or do you tend to just study on your own? How do people prepare for exams? What's your strategies? How does similarity inform your strategy?
I usually study in the same place alone.
Same place alone? Yeah, I would too. How many of you choose the same place all the time? Do you think that helps? How would it help if it helps?
Actually reading something about this, and they were talking about how putting yourself in uncomfortable situations when studying and having lack of similarity, because when you're in an exam, you won't really like have like the music you would have been hearing or like the same space you'd be studying. So it's good to put yourself in unsimilar situations.
Yeah, I can see that. And that's what I was going to ask, is that if you study in the same place and you hope that the similarities can help you remember stuff, wouldn't that all go out the window when you have to show up in an exam room, which is totally different? Do you think there would be any benefit to trying to remove similarity from the studying process? In other words, to study in lots of different places, so that now I can recall this information no matter where. I don't know if it would make a big enough difference I don't think it would really help you game the studying process or to game your exam by studying in different places. But I could certainly see how it could be useful to study across different type of domains. When you prepare for an exam like this one or any, do you find yourself really working to uncover deep relationships? Is that something that's ever emphasized when you prepare for exams?
Sometimes when I'm studying something, then I realize it's gonna be a process, or one thing comes after another thing, like that relationship will kind of make sense in my head.
Yeah.
I don't know that I'm ever working like connect two things that may or may not go together.
Okay, so you might notice it, but you're not necessarily working towards it. Does anybody else find this to be a strategy?
Oh yeah, kind of like I think if you can find a similarity, it can almost be like less things to remember.
Yeah.
Kind of the one thing can branch off into everything instead of knowing each thing individually.
Yeah, so that's another aspect. And we're actually going to talk about this when we talk about experts. And that's the idea of metaphor and encapsulated knowledge. So for a lot of experts, people that are really good at stuff, their knowledge tends to be encapsulated. In other words, you've got a whole group of things that you can access. And once you're in that space, once you've unlocked that, once you're in, let's suppose you're an expert physician. Once you're doing diagnosis, you're thinking about doctor stuff, right? You're not thinking about doctor stuff at home when you're cooking dinner, I hope, but you're thinking about doctor stuff when you're making decisions about patients. That knowledge is encapsulated. But if you happen to be really good at one thing and you notice that there's a parallel structure in a new domain, you can take advantage of that parallel structure and say, this is on the surface very different, but it's like this thing that I'm more familiar with. And that gives you a cognitive structure. That gives you a representation that you can use to help you scaffold some new knowledge. We're going to call that learning by analogy and learning by metaphor. We'll talk about that in future classes. All right, those are good insights. Anything else on this topic? All right, we got 5 minutes left. Let me cover a couple of quick things in 5 minutes. Let's review. What are some reasons to study similarity? Can somebody give me all 4 of them, or at least one of them? What's a good reason?
Underlies important cognitive processes.
Underlies important cognitive processes. What's another one?
Grounded in perception and physics.
Grounded in perception. It's a diagnostic tool.
General.
Domain general. Those are the 4 reasons. There's probably more than 4, but those are the 4 that I listed. And those would be 4 good ones. What are some reasons? What are the 4 main theories? What were those theories that we just talked about? We just talked about them a few minutes ago.
Geometric.
So geometric is one.
Contrast. Yeah.
Contrast.
Alignment.
Alignment. And what was the last one? Transformational models. Here's a good one. What are 3 key assumptions of the standard geometric models of similarity? What were those 3 assumptions? Symmetry was one. Minimality was the other. And the last one? Triangular inequality. So definitely want to be able to name those and possibly define them as well. Which one of the 4 features assumes that similarity is a linear function of shared features as well as distinctive? Which one of those 4 theories was shared and distinctive? Contrast model. This is a great definition of the contrast model. This is a short answer question, but you can easily imagine a question like this being a multiple choice question, where I say, which one of the 4 models describes similarity thusly? And you would just choose one of the 4 models. Okay, if you've got questions, we finished up at 12:07. I said 12:10. That's fantastic, isn't it? It's 12:07. You've got this slide on your slides. You can use it now. If there's anything you want me to talk a little bit more about at the beginning of next week, just let me know what it's going to be anytime. I'll look at them probably Monday night and then adjust my lecture accordingly. See you all next week. Hold on, let me.
I'm not sure, like to state.
Yeah, no, it's very.
Like, sure. She's telling